So okay, so they will prove the following theorem of Dimitrov. December 28th, just before the new year. Well, actually, he sent the proofs to some selected people before this, but this is the date when it appeared on arXiv. And theorem is the following. So alpha, non-zero algebraic integer, not a root of unity, and p, just prime number, any prime number. And then the house of alpha is bounded by log 2 over p squared 1 over d. Well, I had to say what is d of degree d. Here, 1 over the degree. And of course, we can, yeah, I stated for arbitrary p because I think it's kind of like a bit more conceptual, but actually, of course, the optimal case is p equal to 2, and then we obtain simply log 2 over 4, 1 over d. Well, it's certainly not optimal, this constant. There are also, oh, sorry, my cat is hungry. Yeah. I'm sorry, I should give him eat, or he will say this all the time. Yes. Well, just 1 minute. I'm sorry. 1 minute break. Conjectures about what the optimal constant is. It seems that one needs some extra ideas to prove these conjectures, but well, this is already a spectacular result. Because the conjecture, the problem was open since 1965. And well, there are 3 main ingredients. First, the Schoenemann's congruences. Or maybe better say Euler-Schoenemann. So remind you that if we have a polynomial, for use letter t, with roots alpha 1, etc., alpha d, and with in monic polynomial with integral coefficients, then we denote by Fn polynomial whose roots are nth powers of the initial polynomial. also a polynomial with integral coefficients. And Schoenemann's congruence tells that f p to the k is congruent to fp k minus 1 modulo p to the k, meaning that corresponding coefficients satisfy this congruence. In Dobrovolsky argument, so Dobrovolsky used this for k equal to 1. And Dimitrov uses for k equal to. So this is the first ingredient. The second ingredient is the fundamental theorem of Dubinin. This is basically the only deep result that I did not prove. I did not even give an idea how it is proved. So what this theorem tells, we define hedgehog as well, this picture. So this will be, this is A1, this will be, for instance, A2, A3, A4, A5. So here n is equal to 5. It's just the union of straight line segments, all having the same vertex A0 on the complex plane. And Dubinin proved the theorem, which has the following consequence, that the transfinite diameter, I remind, I denote tau transfinite diameter, so of a hedgehog with center 0, is bounded. Well, we have this important reducing factor, nth root of 4, and maximum of absolute values of these numbers. And so this is the third ingredient, the second ingredient. And the third ingredient is theorem of Poya, again related to the notion of transfinite diameter. It's the following. Let K be a compact set on C. And well, I assumed in my exposition, I made the following two assumptions. And well, we denote delta its complement. It starts in the extended half plane, so C C hat. And I used two assumptions that K is symmetric with respect to the x-axis, and delta is simply connected. Well, both assumptions actually are not needed. I received notes by Joseph Sterlet of my course where he just drops both assumptions. Well, but since I assumed them in my exposition, I put them there. In any case, it's efficient. We'll use this with K is hedgehog, and so they're automatically both satisfied. Symmetric hedgehog. Yeah. And let f be a regular function on this delta, on the complement. And its Taylor coefficients at infinity, such that its Taylor coefficients at infinity are integer. If we write Taylor at infinity, so regular on delta means also regular at infinity. So meaning that it is like this. Z, sorry, some B0 and well, the assumption is that these coefficients belong to Z. Then f is a rational function. Oh, sorry. Then what? Yes. And well, assume that the transfinite diameter of our K is smaller than 1. Then f is a rational function. So, in 2 words, if we have a function regular on a complement of a compact and with integral coefficients in its Taylor expansion at infinity, then it must be a rational function as soon as this compact has transfinite diameter smaller than 1. So these are the 3 theorems that rather easily imply, due to the wonderful argument of Dimitrov, rather easily imply the Schinzel Zassenhaus conjecture in the form proved by Dimitrov. And note that all of them are very old. This is basically 19th, early 20th century. So Schoenemann congruence for just mod P was made in early 19th century, and it was extended to higher powers in early 20th century. So it's really very, very old. Theorem of Dubinin is 85. And theorem of Poya is 23. So also very old. So using very classical mathematics, Dimitrov managed to prove a beautiful theorem. We will need 2 lemmas. Both were already stated in my proof of well, my treatment of Dobrovolsky's argument. But first lemma was not completely correct. So let me restate it. So lemma 1. So here alpha, well, we even may assume that alpha is just algebraic number. Well, I assume that it is not a root of unity, but in the new form, in the new statement, this assumption can be dropped. So it is not really important. And p prime number. Then we have one of the following three options take place. First, alpha and alpha to the p generate the same number field. This will be the main case for us. Second, this field is a subfield of degree p. And I mistakenly assumed that when alpha is not a root of unity, only two of these can happen. But actually, even when alpha is not a root of unity, there is also a third option. And third option, there exists a primitive root of unity, primitive pth root of unity, that we denote zeta, right, the word unity. Such that the field Q of alpha to the p is generated by alpha zeta. And it is a strict subfield of Q of alpha. And this is exactly the case when the degree is between, here the degree, relative degree is 1, here the relative degree is p, and this is the case when the relative degree is in between. So, and in this case, in case 3, we have that the, well, if alpha is algebraic integer, because we divide the house only for algebraic integers, but, well, in case 3, in anyway, the house of alpha is equal to the house of alpha theta, alpha zeta, sorry. Well, this is more or less, well, okay, let me, okay. Well, this I think is something that happens in any case because, well, the conjugates, each conjugate of alpha is conjugates of alpha zeta is some conjugate of alpha multiplied by some root of unity. So this is more or less trivial statement. The houses are the same. Okay, so since, well, there is, I uploaded in the folder that where the materials kept, I uploaded a short note proving this, but since well, there was some problem on the first lecture, let me quickly prove it. So we consider the polynomial and it is and then we have what? If the moment wait, sorry. Well, if this polynomial is irreducible, if it is irreducible over the field Q of alpha P, then we have second option. Then simply this means that the degree is for this field over this is P. Now assume that it is reducible. And write it as where, for instance, well, the degree of f is some number r between 0 and p. Then we take, well, up to the sign, the leading coefficient, well, the free term of f, well, not up to the sign, f of 0 is what? Is the product of some roots of this polynomial. But all roots of this polynomial are alphas times some root of unity. So this will be simply alpha to the r times psi. Psi is a pth root of unity. Now we do the following. We take a and b integers such that ap plus br equal to 1. And we consider, well, both f of t, g of t are in the field Q of alpha. And we consider what? We consider alpha to the p a times f of 0 raised to power b. And this again belongs to the field q of alpha p. But it is what? It is, since p plus br equal to 1, this is equal to alpha to some times pth root of unity. And now, if zeta is 1, then this would mean that alpha belongs to q alpha p, and we have option 1. And otherwise, we have a primitive. A bit got confused. So probably I should have said. That we may assume that. Probably I should have said in the very beginning that we may assume that the field q of alpha p is a proper subfield of q of alpha. So let me put it here. Proper subfield of q of alpha, because otherwise we're simply in option 1. Yeah. So if zeta is 1, it's now, since we assume, we simply get a contradiction. And so zeta is a primitive root of unity, and we have option 3. Sorry. So in any case, we have one of these 3 options. So here is the proof of this lemma. And as I said, it is also, you can be found in the file uploaded in the folder. And second lemma, I proved it on the very first lecture. I proved it on the very first lecture that if m and n are integers, m and not plus minus n, then alpha m and alpha n are not conjugate over q. And alpha, here we do assume that it is not a root of unity. Alpha non-zero, non-root of unity. Are not conjugate over q. Okay, so this is the second lemma. And now we can start the proof of the theorem of Dimitrov. of, well, log. Of course, in the statement, I forgot to put log. Proof of the theorem of Dimitrov. So, first of all, let us get rid of the two extra options in lemma 1. So if Q of alpha P, so if we have option 3, of lemma 1, which means what? Means that Q of alpha P is equal to Q of alpha zeta, and it is a proper subfield, it's important, of Q of alpha. Then, well, this alpha zeta has a smaller degree. So by induction in degree, the house of alpha zeta is already bounded by log 2 over p squared 1 over the degree of alpha zeta. But the house of alpha zeta is equal to house of alpha. And the degree of alpha zeta is smaller, so it is bounded by and this is of course strictly bigger than log 2 over p squared 1 over d. And so we're done. Similarly, if we have option 2, of lemma 1, what it means? It means that, again, by induction, the house of alpha to the p oh, sorry, something went wrong. The house of alpha to the p, sorry, always forget to put the log. Is greater or equal log 2 over p squared. And here the degree of alpha to the p is d over p. And this is exactly, and here is equal to the p house, log house of alpha. Of course. And this is exactly what we want. So p here and p here just cancel out and we obtain what we need. So we may assume option 1. We may assume option 1 of the first lemma, which means what? So we denote alpha 1, etc., alpha d conjugates of alpha. And option 1 means that the pth powers are all distinct. This is exactly what option 1 means, that this conjugates the pth powers are all distinct. And so, in other words, the polynomial f, if we denote f of t, or f, the minimal polynomial of alpha, then fp simply is a separable polynomial. And also, lemma 2 implies that fp and fp squared, the polynomial whose roots are p squared powers of alpha, have no common roots. Because otherwise alpha would be conjugate, alpha to the p is conjugate to alpha p squared, and this contradicts lemma 2. Okay, so we have two polynomials, fp and fp squared. fp is separable and they have no common roots, and we consider rational function fp of z. So maybe let me go to the next slide. So we consider rational function u of z as fp of z over fp squared of z. It is a rational function, it is regular, and does not vanish, so non-vanishing. On the hedgehog, on the complement to the hedgehog, h by h, I denote this hedgehog which connects 0 with all the roots of the polynomials fp and polynomial fp squared. So it will be 0, alpha 1p, alpha d p, alpha 1 p squared, alpha d p squared. And also at infinity, it clearly takes value 1. Okay, regular non-vanishing on this hedgehog at infinity takes value 1. This means that we can take pth root of, since it's non-vanishing, we can take pth root of this, and it again will be a regular function, denoted v of z. Well, there are actually pth roots, so we can choose one of them, and we choose the one which takes value 1 at infinity. And this V has three properties. First, it's again regular, because when we take p roots from regular non-vanishing function on a certain simply connected domain, we obtain a regular function. Did they put it? Yes. Regular here. Second, it is not a rational function. And it is exactly because the roots of fp are simple and they are not cancelled out by the roots of denominator. So when we take pth root, we obtain ramification at them. So we cannot get a rational function. Because the roots of are simple and distinct for the roots of the denominator. Distinct from the roots of fp squared. And third property, it has its Taylor at infinity has coefficients in Z. And this follows from Schoenemann. I will give an explanation later. Well, it's very easy consequence of Schoenemann, but I will still give some explanation. And now from these three properties, it follows immediately what we want, because look. Polya, so property one, that it is regular. Well, all the three properties, so polya implies, so it is regular, not rational, and has Taylor at infinity with integral coefficients. So polya implies that the transfinite diameter of the complement of this H is at least 1. Cannot be smaller than 1, because in this case it must be rational. And what is, and Dubinin implies that the transfinite diameter is bounded by, well, what is n here 2d, and the maximum of all these guys of alpha 1 p alpha d p alpha 1 p squared alpha d p squared, which is exactly what? The house of alpha raised to power p squared. So it's only minus. So we obtain, and here d. What we obtain? We obtain that 2 to minus 1 over d, house raised to the power p squared is greater or equal 1. And this is exactly log of the house is log 2 over p squared. So this is the proof just kind of miraculous. And what we are left with is just to speak about the Taylor. So why it has integral coefficients, and here where the Schoenemann takes place, where the Schoenemann plays a role. So what is Taylor at infinity here? So the idea is the following. It's totally standard. So we have the Taylor expansion at 0, this binomial coefficients. And what are these binomial coefficients? It is just 1 over p, 1 over p minus 1, etc., 1 over p minus k plus 1, divided by k factorial, or it can be written as 1 minus p, etc., 1 minus p k minus 1, divided by p to the k factorial. And we know, it's famous exercise that if q is some prime number, then the QAD quarter of the k factorial is given by this wonderful formula. So take integral parts. And when q is distinct from p, then the same argument that proves this formula shows that the QAD quarter of the product in the numerator is greater or equal than this same guy. Well, this is, I think, one of the favorite mathematical Olympiad problems. A rather easy one. And this means that all primes except p cancel out. So they do not cancel out from the denominator. So only p remains in denominator. And this means that 1 over pk is some integer mu k over p to some nu k, where mu k is just some integer. And what is nu k? It is, well, first of all, we have p to the k, and we also have factorial. So it will be k plus nu k of, plus nu p, sorry, of k factorial. Well, it is certainly strictly smaller than k plus k over p minus 1, because this sum, if we make it to infinite sum and replace in integral parts by just actual numbers, we obtain this. And so it is at most 2k. So this is not a series with integral coefficients, but it is a series where the denominators of coefficients are well controlled. It's some small powers of relatively small powers of p. And this means that if we just multiply by p squared, we obtain a series with integral coefficients. Will be what? P2 to k and this is already series with integral coefficients. Note that simply p is not enough because it will cancel only k, but it will not cancel what is left from the factorial. So we do need here p squared. This is why Dimitrov needed congruence mod p squared and not just mod p. Okay, now time to use Schoenemann. So we have fp is congruent to fp squared mod p squared, meaning that fp is fp squared plus p squared times some other polynomial where g is a polynomial with integral coefficients, and attention, its degree, here we have degree d, but the degree of g is at most d minus 1, just because the leading coefficients of p and p squared are both ones. So g cannot have anything in degree d. So it is at most degree d minus 1. And now what is our pth root? We write it like we did, so we obtain 1 plus p squared g of z over fp squared of z one over p. So let us write our polynomials. So fp squared of z, well, let us write it like this: z to the d plus some b d minus 1 z d minus 1 plus etc. plus b0. And let us write our g of z as some c d minus 1 z d minus 1 plus etc. plus c0. All the coefficients are integers. And so we obtain v of z. And we want to get the expansion at infinity. So we write it like this: 1 plus p squared. And here it will be, we cancel out the dth power of z. So we obtain the following: c d minus 1 z minus 1 plus c d minus 2 z minus 2 plus etc. plus c0 z minus d, and divided by what? By 1 plus bd minus 1 z minus 1 plus etc. plus b0 z minus d. Or it can be written briefly as 1 plus p squared z minus 1 certain w of z, 1 over p, where what is w is, well, it's what it should be. and over 1 plus and clearly when we do just the usual manipulations, we obtain that this has Taylor with integral coefficients. Taylor in terms of z minus 1 with integral coefficients. And so our V also must have Taylor with integral coefficients because everything is integral here. So it is some this is an integer, we have seen it. Now z minus k, w of z k. And it also has integral coefficients when we do all the manipulations. So we are done. This completes the proof of the theorem of Dimitrov. Okay. Questions on this part? Well, I think it is well after the work we have done, this was quite straightforward. So perhaps I was a bit too detailed. I could have skipped some passages. Well, so we have half an hour left, and as I promised, I will speak on the theorem of Chris Smith. Well, if the time is left. And well, also. And Smith proved the following, that if alpha is algebraic integer and non-reciprocal, then the Mahler measure of alpha is at least theta, where theta is the real root of t cube minus t minus 1. So, and approximately 1.3247 something. What does it mean non-reciprocal, or what is reciprocal? Means that alpha and alpha minus 1 are conjugate over Q. So if they are not conjugate over Q, so it is non-reciprocal, then Lemma's conjecture holds true, and actually the result is exact, because the Mahler measure of this theta is exactly equal to theta. And well, I want to prove this theorem, so I will not have time, well, half an hour or 20 minutes left. Is not enough to prove this theorem, but I will prove a weaker statement. But which also proves Lemma conjecture, but not with the best possible constant. that the mother measure of alpha is at least square root of 5 over 2, which is, well, actually we can put strict inequality here because this is not an algebraic integer, and mother measure is an algebraic integer. So, and this is approximately 1,118 something. Well, I'm not sure that I put it rightly, but doesn't really matter. Anyway, it's bigger than 1. So it also proves Lemma conjecture for non-reciprocal numbers. But, well, the constant is not best possible. We will use one totally trivial lemma. So let U be a regular function in a neighborhood of the closed disk. And assume and write its Taylor at 0. And we assume that on this disk, U is bounded by 1 in absolute value. Well, it's enough to assume that it's bounded by 1 on the circle, the unit circle. By 1. Then the coefficient say 0 plus the coefficient ak, both raised in squares, are at most 1. For all k distinct from 0. Well, totally trivial lemma because it's just Parseval. So the integral of our function on the unit circle, so we'll write it like this. Is at most 1 because function is bounded by 1. But on the other hand, it is just the sum of squares of coefficients. And so we're done. So lemma is totally trivial. Actually, Smith, in his argument, he obtains some more refined versions of this inequality. For instance, he proves that we don't need to put square here, just absolute value. But, well, for this weaker result, this form is totally sufficient. Okay, now alpha algebraic integer f of z as before zd plus a, I use letters a, okay, ad minus 1, zd minus 1 plus etc. plus A0, or it is the same as, well, we can also factorize it, Z alpha D minus 1, its minimal polynomial. And as we saw in the first lecture, we may assume that A0 is plus or minus 1. Otherwise, the result is simply the lower estimate for the Malor measure is trivial. And now we again consider certain rational function, but now we consider what? We take not fp, we take f minus 1. Or just to be sure, well, I prefer to put here A0. And if I put A0, which is just plus minus 1, so it doesn't change anything, it will be simply what? This guy, Z to D f of Z minus 1. So simply be the same polynomial, but written in the opposite direction. So A0 ZD plus A1 ZD minus 1 plus etc. And again, we consider rational function u of z, which is the quotient of these two. But now, not fp over fp square or whatever, we just take f over and what we know about this function, that u is non-constant. And this exactly because alpha is non-reciprocal. So where we use that it is non-reciprocal, that it is a non-constant function. And so polynomials f and f minus 1 have no common factors. And then we can write its Taylor. Now we take Taylor at 0. So we write it like this. It will be z to the d plus a0 z d minus 1 plus etc. plus a0 divided by, and here I write other way around. So 1 plus a d minus 1 z plus etc. plus a0 z d. And when we do all these manipulations, we obtain 1 plus b1z plus some. And this again will have integral coefficients. So we again have a Taylor with integral coefficients. Well, and at least
Yuri, the one should probably be A0, I imagine.
No, but I multiplied by A0.
No, but in your U that you have A0 in the numerator and a 1 in the denominator as constant term.
Yes. Yes. So, okay, let me put B0 to make it, which is equal to A0. Okay. Well, so just to maybe to get rid of it, I can multiply it by A0 probably. Let me just multiply it by A0. Okay, and then so we just remove. Okay, I remove this, and then this will be what? This will be A0 here and A0 here. And A0 here when we multiply by A0. So let us just put it like this: A0 here and A0 here. So, and then it will be 1. Okay. I prefer to have 1.
Yuri, you have two A0s on the numerator, A0 z to the power d minus 1 and A0 as a constant as well.
Yes, but then A0 squared will give us 1. In the okay, let me return to the previous notation. Okay, let me return to the previous notation, not to confuse. Okay, let me put here B0, but B0 will be equal to A0 as, okay, it doesn't change anything in the argument. What's important that it is plus or minus 1. I don't mind, right? And so what we obtain, since it is non-constant, sum of B1, B2, etc. is distinct from 0 because it's non-constant. And we denote Bk is the smallest. So k is the smallest index. So Bk is such k is such that Bk is non-zero. But B1 until Bk minus 1 are zeros. So we obtain that U of Z is, well, plus minus 1, which is plus Bk Zk and plus terms of subsequent degree. Okay. This is what our Zk, U of Z is. So some plus minus 1, some power with non-zero integral coefficient, and some further powers that we don't care about. Now let us write our U in a different way. What we have with our Z to the D, so f of Z minus 1. Is just Z to the D, Z minus 1 minus alpha 1, Z minus 1 minus alpha D, right? Or if we invest from the z to the d 1z to each of this, we obtain that this will be 1 minus alpha 1z, 1 minus alpha dz. And so our u of z is 1 minus alpha 1z, etc. 1 minus alpha dz divided by, oh, sorry, I put confused denominators and numerators. So z minus alpha 1, z minus alpha d divided by 1 minus alpha 1z, 1 minus alpha dz. Okay. And of course, we will write it as what is called Blaschke product. Yes, so each alpha enters here together with its complex conjugate. So we can regroup the guys and we can write it like this. Z minus alpha I, 1 minus alpha I conjugate Z. It's what is called in analysis Blaschke product. Well, it is an easy Blaschke product, finite Blaschke product. What is nice about these guys is that they are exactly one at on the unit circle, one in absolute value. And we'll write it as some v of z quotiented by some w of z that I'm going to define right now. Note, first of all, that none of alpha is one in absolute value. This again follows from the fact that alpha is non-reciprocal. If alpha is one in if some conjugate is one in absolute value, then it must be reciprocal. Because in this case, the alpha I conjugate, complex conjugate, will be also alpha I minus 1. And this is impossible. So none of these is 1, and we simply split this into guys where alpha I is smaller than 1 and alpha I is bigger than 1. So we denote V of Z just the product, same Blaschke product, but where alpha I is smaller than 1 in absolute value. So Z minus alpha I, 1 minus alpha I bar Z. And we denote by W those which are where we gather alphas which are bigger than absolute value. But since we want to put it in denominator, we reverse them. So we write 1 minus alpha I okay. And so our U, as I said, U is V over W. And now look, And both are regular in the neighborhood of a closed disk, because here the denominators, so alpha I bar is small, so the denominator does not vanish in the disk. And here again, the denominator, since alpha I is big, the denominator does not vanish in the disk. So both V and W are regular in the neighborhood of the unit disk. And well, both are of absolute value 1 on the disk, on the circle, on the boundary of the disk. Well, just simply because every element, they are just Blaschke products, every element of Blaschke product is of absolute value 1. Now, just to simplify, we denote lambda the Mahler measure. And so what it is either the product of alpha I with alpha, oh, what's this? Where alpha I is bigger than 1, and also since the product of all alpha i's, is just plus or minus 1 because it's a 0, we also have that lambda minus 1 is equal to the product of all alpha i's where alpha I is smaller than 1. This is because the product of all alpha i's is, well, up to the sinus alpha is a0, and this is plus minus 1. Well, here I think we should probably plus minus, put plus minus. Here too. And what are these? These are, guys, exactly when we take, when we evaluate our functions at 0. So if we take v at 0, it will be what? Look at v. If we take here 0, then denominators become 1s and numerators become minus alpha i's. So v at 0 is plus minus. It warms my computer. So I need maybe 3-4 minutes. Is it okay, Shauli?
Yes, Yuri.
Yes. Because I want to finish it.
Of course, of course.
Plus minus lambda minus 1. And same for W. If you look, what is our W? Take 0, then numerators become 0, and denominators become minus alpha I, but raised to power minus 1. And this is for big alphas. So again, we obtain lambda minus 1. And what we have that, so since U is V divided by W, we may write it as W is V is W multiplied by U. Well, reasonable. And so let us let V have coefficients C and W have coefficients E. So we have C0 plus C1Z plus etc. So this is our V is equal to what? To E0 plus E1Z plus etc. and times our U, which was B0 plus, I remind you, BK ZK plus etc. So this is our W, and this is our V. And now let us compare the coefficients. And B0, we remember it's plus minus 1. And this is plus minus lambda minus 1. And this is also plus minus lambda minus 1, the coefficients. So what we obtain? Let us take here coefficient CK. CK, when we just do the manipulations, it will be what? It will be E0 BK plus EK, just by formal manipulations with power series. Now, what is E0 BK? E0 is lambda minus 1, lambda to minus 1, and BK is a non-zero integer. BK is a non-zero integer. So this means that E0 BK is at least lambda minus 1. So it is a big number. And it follows that of the numbers of the coefficients CK and EK, must be at least half of this. At least half. They cannot be both smaller than half. For instance, if CK is at least half, and what we have by the lemma that we proved in the beginning, C0 squared plus CK squared is at most 1. So what it gives? It gives that lambda minus 2 plus 1/4 lambda minus 2 is at most 1. And this implies that lambda is at least square root of 5/2 and better. Kind of, well, I must say, for me, it is, this argument is totally miraculous. I see the logic, but I do not understand the idea, what is behind. I must admit, I do not understand. And well, I would be happy if someone explains what really happens here. Because, well, it is a bit, for me, it's a bit like a miracle. very simple argument. Basically, well, out of nothing comes out this quite non-trivial result. Okay, so I think I'm done. So this is all I wanted to say. It's even a bit more than I wanted to say because I found time to prove the theorem of Smith in a weaker form. So, so questions are welcome, and then we're done. So please, if you have.
Thank you, Yuri. Is there any question from anyone?
So there are some questions in the chat, but I must see how to start the chat. Yes, Akash, if f of 0 alpha r needs not be degree. No, it needs to be degree f of 0, I think.
Yes, you are right.
Yeah, I think I'm right here. Yes, well, in Parseval, of course, I should have taken the absolute value in the beginning of the lemma. Yes, Akash, here Akash is right and I'm wrong. Okay, let me correct it. Thank you, Akash. So let me correct it in the beginning in the Parseval. Yeah, of course it should be square. Thank you. Okay. So, well, for me, this argument is a kind of mysterious. I do not really understand what happens here. Okay. More questions? Mm-hmm.
Okay.
Any
So
hope of proving Riemann's? Ricardo asks, any hope of proving Lemma's conjecture by this method? Well, I don't know. You see, 2 years ago, I would have said no because since 71, nobody managed to kind of refine this method to prove Lemma conjecture. Then probably no, because people were thinking. But after the work of Dimitrov, I would really be very careful about denying any possibilities, because the work of Dimitrov itself is kind of beyond any intuition. He did something that, well, you see, on the base of things that were known since long ago, he kind of managed to obtain some non-trivial result. I must say, I really don't know. For instance, yesterday I had a discussion with one very, very prominent mathematician. And I was pushing the point that maybe some refinement of Dubinin would help to prove Lemma conjecture. And he thinks, no, it probably will not be possible. And probably Veselin does not think this either. And this is possible again, because if it were possible to just refine Dubinin and get Lemma, Veselin would have probably done it. Well, I really don't know. So now I'm really afraid of making any predictions. So because things develop in totally unexpected way. Okay.
I have one more question.
Yes.
How difficult is Dubinin's proof?
Sorry.
How difficult is the
well,
proof of Dubinin theorem?
It is well. It is not. Well, it is a kind of hard complex analysis. I think there was some discussion on math overflow, where emerged some simpler version of Dubin's, some simpler proof of Dubin's theorem emerged. And Harry Schmidt made notes where he tried to refill the missing details in this discussion. I must say that even after reading Harry Schmidt text, I still do not, still something escapes me. But well,
are these notes available, or can you upload
yes,
them? In
yes, I can send it. I can even put them on the, maybe I will, they're already on the folder. I put them on the folder.
Okay.
Yes, so so I think it's something like Riemann Hedgehog PDF or something like this you will find on the folder. I think it can be understood. Well, it was done by humans, so another human can understand it. It is, but reading the original Dubin's text looks hard to me. And he also, well, the article, I saw the article, I could not find the Russian version, and the English version is terrible, it's very badly translated. And there is also a book by Dubinin where he gives some more systematic exposition, but again, it's quite hard, but I believe it is understandable. One can try to get it. If say I had here maybe not 4 lectures, not 6 hours, but maybe 10 hours, I could have probably included it if I managed to find it. But of course, within 6 hours, it would be impossible. Okay, any more questions? Tom Ward, you have a question? No? No, he doesn't hear.
No, thank you. Very interesting.
Okay.
Thank you, Yuri, for the very interesting set of lectures. So let us thank the speaker.
Thank you.